but all right. But I can answer some questions, and most everybody missed problem 4. It was kind of tricky. Problem 4 was a concept question about horizontal shifting. So, and also about understanding that increasing on an interval. So if the function is increasing on the interval 3, 8, that means that when x is between 3 and 8, the function is rising, or y is rising. That's what that means. So this problem was testing, did you know the concept about increasing? You know? Okay? And everybody keeps, you know, so these were both x's, not x's and y's. Okay? And then now, so you had to understand what that meant. That the function's rising, that means, and these are x values. This is not an ordered pair, they're x values. And then it says, over what interval is the graph of y equals f of x minus 7? Where is that increasing? So f of x was increasing what? X minus 7. Where is f of x minus 7 increasing? So you had to know that when you subtract 7 on the inside, that's a change in x. It's a horizontal shift because it's on the inside. And which direction does it go? Well, the opposite way you would think. When you subtract 7 on the inside of the function, you're actually shifting right 7. So you have to take these values and just add 7 to them. And 15. Now, if that's not your version, you guys just had different numbers, some of you. This was just one of the versions. Okay, so that's how you do that. Okay, that was 2 concepts. You know what increasing on an interval means, that these are x values, and you know that you're shifting right. Shifting right 7 means you add 7 to each x coordinate. Okay, and so some of you got the right answer, but I wanted a better explanation. I didn't give you half your points back on that one. All right. So, any other questions on this test that you wanted me to go over? I'm trying to think. You know, 5 is a concept question about flipping the thing about the y-axis. And unfortunately, you know, it was using the single points for x-intercepts and not the ordered pairs, but it was a okay. Any other questions? Look over my comments. I did list out, you know, on these test corrections that you should show work and things like that. So if you didn't show the work but got the right answer, I didn't give you too much credit. I mean, you were supposed to show your work on how you got that. This is algebra, we got to show the work. All right. We're going to cover 2.6. And we're doing great in terms of the calendar. Here's our calendar. It doesn't matter that we didn't cover 2.6 here, because we'll cover 2.6 here. We may or may not start on 2.7, and we can cover 2. We have 3 hours each time, and then we wouldn't need 3 hours to review for the test. So we could, if we just did 2.6 tonight, and 2.7 next time, and 2.8 and reviewing, or we could, you know, whatever. We're doing pretty good. We can spend time at the end on worksheets if you want. But you will have to turn in your work anyway, because some people aren't showing their work. Even if we work it in class and I walk around and help you, I'm gonna still have you turn your work in and show me, just to make sure you're actually doing your work. Okay? So let me get this. But we're doing great. Did you guys have a good spring break?
No.
No? Were you sick?
No, I was working.
You had to work the whole time?
And
I
watched
did. I worked a lot.
My son had to work the whole time too. 2.6 is pretty long, and so we may just cover 2.6 today and then work on the 2.6 worksheet. Because
I hate to, did we do a quick little review on multiplicity?
on multiplicity, oh, you didn't understand that.
It's like
Yeah.
how many times did you use? Like,
Multiplicity is the number of times zero is
Zero
used.
used. So like on 2.3,
2.3, I just,
zero would be used one time or,
okay. So the multiplicity, that's fine. The multiplicity, so on the worksheet that was due today, you had x squared and you had x. When you factored it, and x minus 1 squared, right? It's just a 1. So this was your function. So you don't have, all you have to do is you can ignore the exponent and just set this part to 0.
X
So
zero.
x equals 0. And I don't know how you got the negative sign. You didn't need a negative sign. And x minus 1 equals 0, so x equals 1. So the zeros are 0 and 1. The multiplicities you get from right here, the x.
so they won. Okay, excellent.
So it's just 1 and 2. This is odd. And you did have your graph right originally. So cross or touch. So because this is odd, it crosses. Because this is even, it touches and turns around at that 0. It crosses at x equals 0, it touches at x equals 1, and turns around. Okay?
Okay, I see it now. See what it is, the exponent on your x. I didn't even think about that, you know, because it'd be hidden. You just write it as x.
You're right. So it's an
And
understood
I wasn't
exponent. Right.
thinking about it.
Sometimes you need to just go ahead and write those
Yeah,
understood
just go ahead.
ones in there.
So you remember.
Yes. Okay.
Back.
That'll help you. Okay.
Thank you.
No problem. Okay, so section 2.6, rational functions and their graphs. All right. I have a Nearpod for you. So, you like those or not? You don't?
It slows us down.
It does slow us down.
Yeah.
Do you want to do it without the Nearpod? It's nice it has
It's
the
up to
picture.
you. It's
Yeah.
up to you.
I'm trying to think. It does slow us down.
I worked 9 hours today, so.
I sure wouldn't mind getting out early. Oh.
Me too.
Ah. All right. Well, we don't have to use the Nearpod. The Nearpod
It's up to you. You're the boss.
Gives you a chance. We could just do the notes and then work on the worksheets. Okay, let's do that.
It's up to you, really.
No, that's fine.
Don't
We'll-
let me sway you.
Yeah, let's just mod the Nearpod and just do this. I'm okay with that.
Okay.
We'll be fine with that.
All right. So rational functions. It does slow us down. Our quotients of polynomial functions. This means that rational functions can be expressed as f of x equals a polynomial p of x divided by a polynomial q of x, where p and q are polynomial functions and q of x is not equal to 0. So, you know, the word quotient means we're dividing, we're making a fraction. Okay? So this is the definition of rational function. And we need to make sure the denominator can't be 0. So the domain of a rational function is a set of all real numbers except the x values that make the denominator 0. We can't divide by 0. So we'll set the denominator to 0 and see what values would make that 0. And we'll exclude those. And we already did stuff like this in section 1.7, I believe. And so we've already seen this. So we're going to find the domain of each rational function. So you don't need to simplify the function. You have to just set the denominator to 0. This does simplify to x plus 5, but it doesn't matter. The original function has a denominator. You can't let that be 0. So we set the denominator equal to 0. X minus 5 equals 0. We add 5. We get x equals 5. Well, that's what we need to exclude. So we're going to exclude 5. We'll put an open circle there. We have to write this in interval notation. So it's the intervals are of the domain is minus infinity to 5, union with 5 to infinity. We don't use square brackets because we're trying to exclude that value. Okay? Okay, the next one, x squared minus 25. So we set our denominator to 0. And I like to factor this. This is a difference of perfect squares. It always factors, and it's going to factor into x plus the square root of 25, which is 5, and x minus the square root of 25, which is 5. So you should have that memorized, that the difference of perfect squares factors that way. And then you set this factor, x plus 5 to 0, subtract the 5, you get x equals negative 5. Set x minus 5 to 0, you set each factor separately to 0. Add the 5, x equals 5. So those are the values we need to exclude. Negative 5 and 5. I didn't even take roll yet. But I will. So I'll write this domain out and then I'll take roll. Minus infinity to minus 5, the smaller number, union with, don't forget the middle little section, minus 5 to 5, union with 5 to infinity. Okay, let me take roll. And while I'm taking roll, I will pause the recording and let me remind me to start it again. Oh, apparently. Okay. Today is March 7th.
Right. 14.
The 14th? Oh, why didn't I take roll on the 7th? Was that the test? No.
We didn't have class on the 7th, did we?
Oh, that was spring break. Oh, I'm so confused. Okay.
Throws you off, then.
It does. And usually I have, if I, tomorrow it's supposed to get up to 50 and melt all this, but. Okay. So, all right, so this is how we find the domain. We've done this before. So we'll set this denominator to 0. X squared plus 25 equals 0. Subtract the 25. X squared equals negative 25. If we take the square root of both sides, X equals plus or minus, you have to add that plus or minus, is 5i. If it's not a real number, it doesn't have any zeros. It's not a real number. So there's no zeros, no numbers. You can't find a number that you're going to plug in and square and add 25 to and get 0, unless you use an imaginary number. And imagine, so, and here's what the denominator looks like if you graph it. Here's the x squared plus 25. 25 is up here. It's a parabola opening upward. It doesn't cross the x-axis. It can never be 0. So there's no restrictions, so the domain is minus infinity to infinity. Okay? All right, now we're going to talk about the most basic rational function now. It's the reciprocal function. And it's defined by f of x equals 1 over x. The denominator of the reciprocal function is 0 when x equals 0, so the domain of f is minus infinity to 0, union with 0 to infinity. We've got to exclude the 0. If you put in 0 for x, you'd be divided by 0. And here's the picture of it. We're going to go over just a little notation on the next page. Okay, there's a picture. This is the most basic rational function. We're going to just look really quickly at this. This is for the function f of x equals 1 over x. It was on the previous page. It looks like this. We haven't covered these, but these are asymptotes. This is a horizontal asymptote at x at y equals 0. This is a vertical at x equals 0. We're going to be covering these in a second. But anyway, if you look at these, this is some notation just. We're going to look at the behavior of the function f near the excluded 0. We have to, this 0. As x approaches 0 from the left, going here. And this is how you write it. X, arrow, 0 to the negative. That means from the left. F of x is going to what? Negative infinity. So, this is what that means. Here's the word. That is the graph fall. Okay? If we look at it as x approaches 0 from the right, here's the symbols. X approaches 0, and there's a plus sign up here, that means from the right. Then f of x is going to positive infinity. And you're going to find out that's the definition of an asymptote. And then this is just explaining this notation. You might need it later in calculus or something. But if you look at the behavior of f as x gets further from the origin, as x goes to positive infinity, our f of x is going to 0. That's how you write that. That is, it increases without bound. As f of x approaches 0. Okay, here the next one, I think x goes to minus infinity, f of x is going to 0. And here's the notation. As x goes to minus infinity, f of x goes to 0. Here's the words. Negativity, negative infinity. I never even noticed that typo. Negativity. Okay, I don't even know what negativity is a word, but all right. So that's just that notation. I'm not going to test you on that notation. I think they use that notation to explain the actual definition of a vertical asymptote. That's sort of why I went over it. But see, if you're looking at this notation here, going, what does this mean? So the line x equals a. This is the definition of a vertical asymptote. Remember, x equals a constant is a vertical line. A vertical asymptote is a vertical line, and you need the x equals part. It's a vertical asymptote of a function f if f of x increases or decreases without bound as x approaches a. This is the definition of a vertical asymptote. So it can happen in all these different ways. They're showing as x approaches a from the right. If f of x goes to positive infinity, then x equals a is a vertical asymptote. If x goes to a approaches a from the left, and f of x goes to positive infinity, this is a vertical asymptote, x equals a. And then we can have approaching from the right and going to negative infinity, decreasing without bound. And then from the left and going to negative. These x equals a in all these four cases will be a vertical asymptote. So just says, so that's the definition of a vertical asymptote. What we really need to know is how to locate these things. It's important that you know what it is, and that is the equation of a vertical line, and the graph can never cross its vertical asymptote. So how do we locate vertical asymptotes? Here's what's important, the most important of this. We have f of x is p of x over q of x is a rational function. And what we're saying is that p of x and q of x have no common factors. So and a is a 0 of q of x, the denominator. Then x equals a is a vertical asymptote. And we will abbreviate that VA. And when finding your VA, f of x, so f of x must be in simplest form. So it said there were no common factors, so we need to factor first, then cancel. And so f of x, so we factor first and then cancel. If anything cancels out of the denominator, those are not asymptotes. In fact, if there's a value of a that causes the denominator to be 0, but in reduced form, it does not cause the denominator to be 0, then there is a whole corresponding to x equals a. So these are vertical asymptotes and wholes. Okay? So, here's a function. F of x equals x over x squared minus 1. This is the difference of perfect squares, so we're going to factor it. We want to factor and see if anything cancels. We really like the difference of perfect squares here. It's x plus 1 and x minus 1. Boil that out. See that is true. Memorize how to find factor of the difference of perfect squares. Anyway, you can only cancel factors. You can't cancel this x with that x because this is connected to a 1. There's no x plus 1 in the numerator or x minus 1. Nothing cancels. So, nothing cancels. So, because nothing cancels, there are no holes. So we're going to set our denominator to 0, and these will be the vertical asymptotes. So x plus 1, we already factored it, let's set that to 0, equals 0. So x plus 1 equals 0, or x minus 1 equals 0. So we subtract the 1, we get x equals minus 1. And we add the 1, we get x equals 1. So we have vertical asymptotes at x equals minus 1 and x equals 1. That's our answer. There's no holes if I ask about holes. Okay, so we'll do the next. Any questions? So that's how you find your vertical asymptotes. You can't divide by 0. That's what makes a vertical asymptote, but sometimes it's a hole. So we'll show you some examples of that. But look at this one. We have x squared plus 1 in the denominator. That doesn't factor. You guys believe that that doesn't factor? X squared plus 1? X squared plus 1 doesn't factor. If you try to factor it, here, I'll just write this out. I don't know if you can use that or not. So, x squared plus 1 is not, x plus 1 times x minus 1. Because if you FOIL that out, you get x squared minus 1x plus 1x minus 1. You get x squared minus 1. And x squared plus 1 is not x plus 1 times x plus 1 because you've forgotten the middle term. FOIL that out, you get x squared plus 1x, that's the outer term, plus another 1x plus a 1. So that's x squared plus 2x plus 1. That's not equal to that. So this does not factor. So we also we could just show that you could try to take the square root of both sides on it. We'll set it to 0. We will set it to 0. Anybody need that? Okay. You understand that that doesn't factor. That's a common mistake, thinking that that factors. Okay. It's a difference of perfect squares that factors, and you have to have a middle term to be a perfect square trinomial. Okay, so we set our denominator to 0, and I showed you that this doesn't factor, so we couldn't reduce anything, so nothing cancels. cancel anything. You can't cancel an x and an x here. You only cancel factors. This didn't factor. So if we subtract the 1, we have x squared equals negative 1. That means x equals plus or minus the square root of negative 1. It's not real. It's not real, so it doesn't, you can never get it to be 0. It doesn't cross the x-axis. It's like the parabola like this up at 1. The denominator here, you can't square a number and add 1 to it and get a negative number or 0. You can't, you're adding. So that doesn't factor. So there are no VAs then. That's the answer. If it doesn't factor, and if you get an imaginary number, this would be plus or minus I. It's not real. It doesn't cross the x-axis. The denominator can never be 0, so there are no VAs. Okay. All right, let's do the next one. Example, if you're ready. Okay, so all right, the denominator factors, and it's a difference of perfect squares. So it factors into x plus 1 and x minus 1. And there is an understood 1 here in front of the x minus 1. So we can cancel the factors x minus 1. But you're not left with 0 on the top. You're left with a 1. There's an understood 1 there. So we write 1 over x plus 1. It's simplified. So to find our VAs, we set our simplified, you do have to set the simplified denominator to 0. X plus 1 equals 0. So x equals minus 1. We have a VA at x equals minus 1. Okay, and if you set the, if you find your holes by setting the canceled factor to 0. So x minus 1 equals 0. So x equals 1 is there's a hole at x equals 1. If I asked about holes. So, okay, and if we could graph that, if we graph that on the calculator, we can graph the original function on the calculator. Y equals clear. Okay. You have to graph it. We're going to graph the original function. You have to put parentheses here and here. If you don't add parentheses, you're going to get it wrong. And if you were to try to graph it in this form, you would have to put an extra set of parentheses around the whole denominator. Otherwise, I'd think this is in the numerator, you know. But we're just going to graph it from here, the parenthesis, x minus 1, close the parenthesis, divided by parenthesis, x squared minus 1. All right, and we're going to hit zoom 6 for standard. See what that looks like. Okay, so this has a vertical asymptote at x equals minus 1. So if I draw the graph right here, at minus 1 we would label it BA at x equals minus 1. We draw the vertical asymptote or horizontal asymptote with a dashed line, and this function looks like this. And this is actually a horizontal asymptote. We haven't covered that yet. At y equals 0. Y equals a constant is a horizontal line. And then this half of it is going like this. So the graph cannot cross its vertical asymptotes. That's how the calculator graphs it. This is how you have to graph it, showing your asymptotes and labeling them, and don't make it look like it's got a solid line between them. Okay? Now, so we can see that x cannot be -1. That's a vertical asymptote. What about 1? We have to look at the table for that. We can't see they don't put a big old hole right here, the circle, on the graph. We have to go to the table. Second table. Oh dear, the table's not set up. Second table set. I want it in automatic mode. Second table. If we look at +1, the whole, so really this is -1, and at +1 there's a hole here. There'd be a circle there. And it says error on your calculator on the table. It says error for the vertical asymptote, and it says error for the hole. Because we'd be dividing by 0. You always have to look at the original function. And then, if we simplified it to 1 over x plus 1, we do have to say that x can't be what we canceled out, 1. Then, of course, x can't be -1 either, but at least we got rid of where you could see that was the case. So we have to look at our original function. All right, and then the last example, any questions? Okay. We're going to factor this one. So k of x is x squared minus 4. X squared minus 4 factors into what? X plus 2, x minus 2. You should have that memorized. Am I too far down? That's over, and put parentheses around it, x minus 2. So we cancel that, and we get just x plus 2, but we can't let x be 2. And that's the whole. We have a whole at x equals 2, and we have no VAs. What does the line x plus 2 look like? Well, we start at 2, we go up 1 over 1, it's just got a slope of 1. And at 2, we would have to have a circle. That's what that would look like. But we could only see the error on the table.
If we put that in the calculator. If you put in x plus 2 in the calculator, you won't see that error. But it's not just x plus 2. We have to put the original function in. You would just put parentheses around these things and divide it by. And you could see it on your table, that error. Okay, so that's 4 examples.
One of them had no vertical asymptotes. Oh, guess what? It also had no holes. That's okay. First one had no vertical asymptotes. This one down here had no vertical asymptotes, no holes. This one had no holes, but it had 2 vertical asymptotes. This one had 1 vertical asymptote with 1 hole, and this one had no vertical asymptotes, but it had a hole at x equals 2. So that's how you find vertical asymptotes. Okay. So we're going to talk about the definition of a horizontal asymptote next. Let's see. Aha. I had made some copies of section 2.6 worksheet. Let's see. These are just sitting in my these are just sitting in my drawer. So if you haven't printed it yet,
And the homework,
that's the homework that's due.
I have one.
Oh, you already printed it?
Yeah, I have it. I'm pretty sure.
Yeah. That's front and back. So we've gone over how to do number 1 and 2 so far. There you go. Okay, so that's the homework for next time. We've gone over how to do this one and this one. You have to factor that instead of 0, the denominator. We know how to find vertical asymptotes and holes. We haven't covered slant asymptotes yet. Okay, so here's how you locate horizontal asymptotes. It's cold in here tonight. All right, the definition of a horizontal asymptote is a line y equals b. Remember, it's a horizontal line. The equation of a horizontal line has y equals a constant. We're going to say it's y equals b, where b is a constant. It's a horizontal asymptote of the graph of a function, f, if f of x approaches b as x increases or decreases without bound. So here's the pictures. It can go like this. It's approaching y equals b, and it never could, well, and it actually is approaching it here, and it's approaching it this way, and it could actually cross it over here. So here's a note. A graph can never intersect a vertical asymptote, but it may cross its horizontal asymptote. So here's a picture. We've got a horizontal asymptote, but it's crossing it back here. And here's the rules for locating horizontal asymptotes. And you're given these rules on the formula sheet for the next test. So here's, remember, f is a rational function. F of x can be written as a polynomial function, p of x, divided by a polynomial function, q of x, where q of x can't be 0, because we can't let the denominator be 0. So we've written these out. The these with n's and these with a sub n minus 1.
The coefficients, the exponents. So the degree of the numerator here, n is the highest power on the numerator, is n. The degree of the denominator is the m. The degree is the highest degree of the numerator or the denominator. That's the degree of each polynomial. And so what we do is we just have to look at the function and recognize, take what the degree of the numerator is and what the degree of the denominator is. If the degree of the numerator, n, is less than the degree of the denominator, m, then the x-axis, or you will want to write it in terms of its equation, y equals 0, is the horizontal asymptote of the graph. If n equals m, then the line y equals the leading coefficients of both numerator and denominator is the horizontal asymptote. If n is greater than m, the degree of the numerator is greater than the degree of the denominator, the graph has no horizontal asymptote. So those are the three cases. So we're going to have the three cases as examples. So so here's a note. Unlike identifying possible vertical asymptotes or holes, we do not put f of x in the simplest form when determining horizontal asymptotes. So we do not need to factor, and we do not need to cancel. In fact, if we factor and cancel, we won't get the right horizontal asymptote. Or we may not. So look at f of x equals 9x squared divided by 3x squared plus 1. What's the degree of the numerator, or the top of the fraction? It's 2. What's the degree of the denominator? It's also 2. So we follow the rule number 2 up there that says if the degrees are equal, y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator is the horizontal asymptote. So here's our coefficients, 9 and 3. So it's y equals 9 divided by 3, or you simplify that to y equals 3. So we have a horizontal asymptote at y equals 3. We just followed that rule. You just follow that rule. So you need to be able to identify degrees. Does everybody understand degrees? And then compare them. And are we saying that this function equals 9/3? No. That function does not simplify to 9/3. We're saying that's the equation of the horizontal asymptote. And the slideshow that goes with this actually shows this graph and shows you the horizontal asymptote. So the slideshow, either it's in Shobi or it's in my Nearpod, but it actually shows these graphs. So it's kind of nice to see those graphs. We could graph it on the calculator ourselves and see it. Do you find that helpful? We can graph that. I'll graph this first one. So you do have to put this in the denominator in parentheses. So you're going to turn it on, second quick, y equals clear. I don't have to put the numerator in parentheses because it's not two terms, just one term. So it's 9x squared. It wouldn't hurt to put it in parentheses if you're not sure. Divided by, now you do have to put the denominator in parentheses. 3x squared plus 1. The trick might be to get the correct window, but we'll see what the window looks like. Oh, yeah, that works. Okay. This window's fine. The line y equals 3 is up here at 3.
this is what that graph looks like. So, if you were to draw that graph, 1, 2, 3, you put a 3 here, you draw a dashed line for your horizontal asymptote, and you would label it HA at y equals 3, and then I'm not sure, I'm just doing a sketch. This will go like that, and this will go like that, and symmetrical. That's how you would draw it. It actually is not crossing the line y equals 3. Okay? Did you get that on the calculator? Alright, so don't have to simplify, don't have to factor. In fact, these things don't factor. All you do is there's an understood exponent of 1, watch that, okay? N, the degree of the numerator is 1, M is 2, the highest exponent on the denominator is 2, N is less than M, so we follow the rule number 1. Rule number 1 says the x-axis for the line y equals 0. So we have a horizontal asymptote at y equals 0. So we're going to graph that. That wouldn't be too hard to graph. We're going to just change this a little bit. Y equals, instead of an x squared on top, you just delete that. And everything else is the same. Let's graph that. Just one little change and look what happened to it. Okay? So, let's draw what that one looks like here. Because this is the x-axis, I'm going to continue it with dashes and say HA at y equals 0. This dashes over here. Looks like it's going like this. Is that negative? I don't know. We're just drawing a sketch. Go something like this. And it keeps going. But out here it doesn't cross the horizontal asymptote, but here at the origin it did. It crossed it right there. Okay? So that had a horizontal asymptote. No vertical asymptotes. Why doesn't it have any vertical asymptotes? Because 3x squared plus 1 can never equal 0. You set it to 0, you subtract the 1, you're going to have, and divide by 3, you get x squared equals minus a third. You can't square something, you get a negative number. So there's no vertical asymptotes on these examples. These are just having horizontal asymptotes. All right. Any questions? Does that make sense? All right. Then the next one, just look at the degree of the numerator. N is 3. M is 2. N is greater than 2. So, N, which is M. N is greater than M. We follow this rule. And we write no HA. And box it in. We don't leave it blank. Because I'll think you didn't understand it. So you do, and I say in the direction, tell me if there's no horizontal asymptote. If there's none, write none or no HA. That's what you want to do, is always be clear. N is greater than M. So you're just following these rules. As long as you know how to find the degree denominator, you're fine. And follow the rules.
Makes sense? Okay. All right. We're on slant asymptotes. So these words down here say that if n is the degree of the numerator, if n equals m plus 1, there is a slant asymptote. And we'll abbreviate those SA. N's the degree of the numerator, m's the degree of the denominator. Remember, this is all about rational functions. We have numerators and denominators with x's in them. So the graph of a rational function has a slant asymptote. If the degree of the numerator is 1 more than the degree of the denominator. If n is 1 plus n. This is what it looks like. Those words translate into this equation. The equation of the slant asymptote is found by using division. After dividing, we'll drop the term with the remainder, and the equation then of the slant asymptote will be y equals mx plus b. And we're going to use synthetic division. Synthetic division, I'm going to show it to you. It's for dividing by x minus a constant. There's a minus sign there. Okay? So, I don't know if I brought it with me. The synthetic division is one of the sections we skipped. Skip sections 2, 4, 2, 5. If you want to look back at those sections to understand synthetic division again, but I'm going to teach it to you. So, if we want to divide this using synthetic division, we rewrite this numerator with every place. So we're going to rewrite this. F of x is going to be, it has to have an x squared term, and its coefficient is an understood 1. And then the x term is going to be 0, so we're going to write that down, and then plus 1. You have to have each term with a coefficient, and if a term's missing, it has a coefficient of 0. And because we're dividing by x minus c, x minus 1, our c is 1. The signs match. So we put our c in this box. This will be our c. And then we write the coefficients of, so 1. This equals 1. We'll just put 1 in the box because it's positive 1. We write our coefficients here. Okay. Now, the way this works is we're going to add going down. So 1 plus 0 is 1. And then we're going to multiply to find this number. So 1 times 1 equals 1. We do 1 times 1, we get that. And then we're going to add
0 plus 1, and we get 1. Then we multiply again. This is a 1 times 1 equals 1. And then we add 1 plus 1 is 2. And this is always going to be our remainder. And if we're dividing x squared term by highest power of x, this is going to be your x term, and this is going to be your constant. So the slant asymptote at y equals 1x, and this was positive, so it's plus 1, or y equals x plus 1. You can drop the understood 1 if you want. That's how you can find your slant asymptotes. If you want, I can divide it out by hand. Or we could just do another example. You've got the example where you have to find the slant asymptote on number 3 on your worksheet. This is finding a slant asymptote. So let's do one more example of this way. So we are actually dividing these let me write out what this means. When we take f of x equals x squared plus 1 divided by x minus 1, we are actually getting that it equals x plus 1, and then we take the remainder and put it over the divisor, what we divided by. That's what this division equals, but this part with the y equals in front of it is the slant asymptote. And we can just drop the remainder. This is the slant asymptote. This isn't equal to that, but it's the slant asymptote. Okay, let's do this other example. So the thing is, with synthetic division, we're dividing by x minus c. So this has a plus sign, so we have to rewrite that as x minus a negative 2. So our c is negative 2. So we have to put negative 2 in the box. And then we put 2, negative 5, and 7. This is already in descending order. It has to be in descending order, and we can't miss any terms. And there's none missing. Then we draw a line. And there's nothing here, so 2 plus 0 is 2. So we just bring that 2 down. Then we do negative 2 times 2. All right. So it's negative 2 times 2 is negative 4. Then we add, that's negative 9. Then we do negative 2 times negative 9 is positive 18. And then we add 7 plus 18 is 25. This is our remainder. This is our constant term. This is our x term. And this is the kind of problems you'll see on a test. It won't be x cubed, or we won't be dividing by something squared, or so the the slant asymptote at equals 2x minus 9. That's our answer. So this is synthetic division, and I can show you, if you'd like to see it, how you would divide this by long division with algebra. And it might help you just to see it once so that you know. I don't know. What do you think, guys? This is kind of magical. This is much easier than the other way. So I'll show it to you when you're ready, because you want to see it once so you can decide, do you want to do it this magical way, or do you want to do it the long way? If you only understand the long way, then you certainly can do it the long way. So let me show you how you would divide this one the long way. Are you done writing? Alright, so if we go back up to the original problem here, for long division, we're going to put our divisor here, and then we have to put this with every, in descending order, with every term accounted for, with the extra 0 in there. So I'm going to put the understood ones too. Alright, and we're going to divide this by hand. So the first thing you do is you say, what times x equals x squared? 1x squared. And x, so you can put an x here. And then you're going to take x times x minus 1 and distribute that. You have to take x times this whole thing. You get x squared minus 2x. So you put that under the like terms. Okay? And then in long division, at this point, you need to subtract. But to subtract polynomials, we'll put parentheses around the whole thing and put a subtraction sign. We usually like to make that addition and change the sign of every term and add. So that's what I just did. So 1x squared minus 1x squared is 0, and that was supposed to cancel. And 0 x plus 2x is 2x. That's it. And then we bring down the plus 1. Okay? Now what we say is what... Okay, we're looking at this. What times x equals 2x? A positive 2. And then off to the side, we're going to take 2 times x minus 1. Distribute it. 2x minus 2. And then we need to subtract, but to subtract, we like to put the subtraction sign. You would need parentheses, and then you're going to change this to a positive and change the signs and add. That's the way we like to do it. We get 0 there, and you take 1 plus 2 is 3. So you get x plus 2 plus 3 over x minus 1. And this part, did we get the same thing as when I divided?
Wait a minute. How did I get a remainder of 3? Did I do something wrong, guys? I don't know. We're supposed to come out the same. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 1 plus 1 is 2. What did I do here? Oh, no. I'm supposed to get 2. I don't know. I made a mistake, guys. And I'm too tired to figure out what it was. I don't know if you see it, but I brought down the 1. I don't know what I did. I made a mistake somewhere. The remainder was supposed to be 2, but I have it worked out somewhere, but I don't know if I brought it with me. No, didn't bring it with me, but all right. It bothers me. Okay. X. Oh, I made a mistake. That's why. Very much so. Okay. Does anybody else see it? What is x times x? X squared. What is x times minus 1? Okay, so this is a 1, and this was 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 a 1, and we got 2. We had to do 1 times x minus 1. Sorry. So we do get the same thing. So it's x plus 1, and this is 2. Okay, clear as mud, right? So, but anyway, if you're, that's the process. I don't know, do they still teach you guys long division in school? Like, if you're going to take 25 into 716, the process to do that. You say, what times 25 equals 7? It doesn't go into 7. So what times 25 equals 71, the closest without going over? That's 2. So you put it over the 1, then you do 2 times 25 is 50, and then you subtract, and you get 21. 25 doesn't go into 21, otherwise we use the wrong number there. Then you bring down the 6. 25 goes into 216. How many times? 8. That's 200. And then you subtract, and you get a remainder of 16. So that means that 716 divided by 25 equals 28 plus 16 over 25. Or a mixed number, 28 and 16 25ths. And that's how you do long division. And so if you're going to do it this way, you do the same process, except instead of subtracting, I like to change it to addition. If you keep it as subtraction, you make sure you subtract each term. We don't have terms over here. It was pretty simple to subtract. But here we had terms, so that's why I changed it to positive and distributed that minus sign. So that's long division. You can do it either way, but it's easier to do synthetic division. And you're allowed to use synthetic division. You just would show that work. So, all right. We're going to take a break and we can continue. You can
work on that, you can work on that first page of the worksheet. You want to take a break and see, take a break and then come back and work on the first page, and then I can cover the rest of 2.6.
I'm gonna
Stop.